energy particles, molecules, other things. So I will speak about beautiful graphene, about photonic crystals, about Schrödinger and Dirac billiards. I will introduce you to that particular language and their spectral properties. So the talk will be divided into several parts. So, stand here. First, let me say something about graphene and microwave billiards. Secondly, what we understand about the Dirac spectrum in a photonic crystal. That means I will give you the experimental setup. Then I will speak about transmission and reflection spectra. Then we will put a photonic crystal in a box. Then we have a Dirac billiard. Again, I will show you measured spectra, the density of states, and the spectral properties. This is work done within a collaborative research project called Sonderforschungsbereich. And here you see in blue the members of my group. And we have had and we're having a very strong interaction with Norbert Petrala, Lorenz von Smeka, and Jochen Wambach, my esteemed colleagues in Darmstadt. So then I will give an outlook. The Nobel Prize in Physics in 2010 was given to these two gentlemen, Andrei Geim and Konstantin Novoselov. And it said for groundbreaking experiments regarding the two-dimensional material graphene. So let me start the talk about what Katznelson in Materials Today said in 2007. He said what makes graphene so attractive for research is that the spectrum closely resembles the Dirac spectrum for massless fermions. And we are going to model this in our experiments. Now, the honeycomb structure of graphene, the red and the blue points are carbon atoms, can be seen. These are two triangular sublattices of carbon atoms. And the band structure, that means the energy as a function of quasi-momentum Kx and Ky, shows a conductance band and the valence band. And here you see the beryllium zone. Here, each corner of the first beryllium zone. The electron energy, denoted here by E, later on by omega, also has a conical dependence on the quasi-momentum. So you see all these cones here. And the points, where K and K prime, are the so-called Dirac points. I will speak about this in some detail later. The energy, which is plotted in this direction, is given by h bar times the Fermi velocity times k, and it's low in graphene. It's c, velocity of light over 300. That means graphene is a strongly interacting system. And we realize graphene in analog experiments of microwave photonic crystals. So let me define what I understand when I speak about microwave photonic crystals. Let us look at the right-hand side. Shown is here a microwave billiard, a quarter of the stadium. It's a highly chaotic system, but let's forget about this. And this has three antennas on top, and we are feeding microwaves in one of these antennas, measure the reflected power, or we feed in microwaves in one antenna and couple it out in another antenna. Then we speak about transmitted radiation. If the height of such a resonator, which we also call the billiard, is smaller than the wavelengths of the microwaves put in there, then the distribution of the microwaves inside the cavity is given by the scalar Helmholtz equation. Second order derivative, differentiation k squared Ez. And we can see that this equation is fully equivalent to the Schrödinger equation, which we would have in the so-called quantum billiard. we would have a potential put on the green felt, so to say, of the billiard. Then the energy is not continuous, but we have a quantized energy. And so there's an analogy between the Schrödinger equation and the Helmholtz equation for billiard. And therefore one speaks about these billiards also of Schrödinger billiards. Later on, we will speak about Dirac billiards as well. So the physics is, here we can determine the wave number, which is directly proportional to the frequency. In the quantum problem, we determine the eigenvalues, and the electric field strength Ez corresponds to the eigenfunctions. So by doing measurements in these microwave billiards, we are really trying to understand the quantum billiard and the Schrödinger problem for any physical system which we can model. So that's the measurement principle. That's a microwave billiard made out of niobium. Since we are doing these measurements also superconducting, in order to have the highest possible resolution. So the microwave power is coupled in, and it's taken out at another antenna, as I said earlier. And the outcoupled power over the incoupled power, it gives the square of the modulus of the S matrix elements. We can not only measure the S matrix elements, but also the faces of the S matrix elements. So we have a resonance spectrum where we plot this quantity, P out over P in, as a function of frequency, and we see single resonances, and we can count these resonances and get the resonance density. Wherever there's a resonance, delta P, then we have the resonance density. And this resonance density has a smooth part. It's called in resonators usually while. The while term, it's a smooth part of the level density, and it has a fluctuating part. And if we do the Fourier transform, and we go from the frequency space into the length space, then this is accomplished by arriving at Gutzmüller's trace formula. Then we get the length of the periodic orbits in the spectrum. So in order to have this analogy between resonators and the real quantum system, we have the open flat microwave billiards, and that's a photonic crystal. A photonic crystal is a structure whose electromagnetic properties vary periodically in space, for example, with an array of metallic cylinders. So that's an open microwave resonator, and here you see two plates, a bottom plate with these resonators, and a top plate which closes then the billiard. And a flat crystal resonator means that the electric field is perpendicular to the plates. That means we are investigating so-called transverse magnetic modes. And the propagating modes, as I have just shown you, are solutions of the scalar Helmholtz equation. And that corresponds to the Schrödinger equation for quantum multiple scattering problem. And the numerical solution yields the band structure then of this photonic crystal. And that band structure, as we will see, is fully equivalent to the one of graphene. So let's look at the calculated photonic band structure. The dispersion relation omega of k of a photonic crystal exhibits a band structure analogous to the electronic band structure of a solid. So here are the honeycomb structures, the crystal, the scatters inside the billiard have that structure. And if we do the calculation, then we get this, what I showed you earlier, that the triangular photonic crystal possesses a conical dispersion relation. That is, has a Dirac spectrum with Dirac point where the bands touch each other. We will later on use this notation, gamma k and gamma m, and these different points are defined in a moment. These are the points, if you look at the Bragg zone. So the voids here, the voids, the black points, form a honeycomb lattice like atoms in graphene. Next, how does the effective Hamiltonian look around the Dirac point? So close to the Dirac point, the Hamiltonian is a 2 by 2 matrix. Omega d, the frequency at the Dirac point, enlarged here, is plus Vd, that's velocity, the group velocity at the Dirac point times dkx, sigma x plus dky, sigma y. dkx and dky are the quasi-momentum components in x and y direction. If we substitute these by the respective differentials, then we have the Dirac equation. As we had the Schrödinger equation before, at this point we have the Dirac equation. So the experimental observation of the Dirac spectrum in open photonic crystals happened in 2010, and this is where we published it. Let me describe you how we did this. That means we describe now the scattering experiment which we did. We used a source, a so-called vector network analyzer, and we had an emitting horn antenna in order to get plane waves. The plane waves were put onto the crystal, consisting of over 800 cylinders, and we received the scattered waves as well as the transmitted waves through this crystal. And so the horn antenna emits approximately plane waves, and the vector network analyzer measures that ratio outcoupled power over incoupled power. That means the square of the estimated domains. We can measure transmission spectra. That means we go in antenna B and come out in antenna 1, or go in antenna A and come out in antenna B. Or reflection spectra. That means we measure the reflected power on antenna A or antenna B. So the experimental realization of a two-dimensional photonic crystal is shown here. It's quite a large object. It's about a meter times a meter. And we have the following numbers of cylinders, 874 cylinders. Cylinder radius of each of these cylinders is 5 millimeters. The lattice constant is between cylinders is 20 millimeters. The crystal size is quite large. And the cutoff frequency when the system becomes three-dimensional is 19 gigahertz. So we really have a flat resonator up to 19 gigahertz. The first step was the experimental observation of the band